Welcome back to E340, Introduction to Computational Bioengineering, Dynamics of Networks. This is lecture 5, and we'll continue our conversation about optimization and parameter fitting. Last time just a quick reminder, the class is being recorded and live streamed on YouTube. Last time we discussed a little bit of what the intention of SIR models is in terms of modeling a specific epidemic where individuals develop long-lasting immunity, and we talk why SI models are sometimes insufficient to, or SIS models are sometimes insufficient to explain some of these types of diseases and epidemics. And we looked at what indicators of the dynamics of the pandemic are in terms of how identifying when the pandemic is or the epidemic is starting to decrease, how the maximum number of infected individuals depends on the parameters of the SIR model, and so on. We finished class with a very quick overview of what parameter estimation is. We'll come back, we'll pick it up there today and continue talking about how to use computational tools to infer or determine what the parameters of an SIR model are, provided that we have access to some data about how the epidemic is spreading in the population. As I mentioned, the SI model that we looked at is at the beginning of the class is insufficient to explain certain types of diseases, especially those epidemics or diseases where individuals develop long-term immunity. At least when we last year when we were discussing this class, by this time we really didn't know how long immunity was for COVID-19. We sort of like, even though we knew there would be a couple of waves associated with new infections or previously susceptible individuals that get infected at different times throughout the year. We didn't actually know how reinfections were, how likely reinfections events were. Now it seems that we have a little bit of data about it. Seems to be, for example, more common than some other diseases, but it's still not super common to be reinfected with COVID. So when we looked at the data at that time, we were just going through the first wave. So that first wave was the SIR model was a good approximation at that time of what the epidemic was looking like, at least in the US. Again, the idea behind the SIR model is that individuals belong to 3 different compartments. Either they are susceptible, infectious, and recovered. And there are some rates that determine how individuals transition from this or between these compartments. And the parameters of the SIR model determine the rate at which these transitions occur. The important parameters are N, gamma, S naught, and mu. Um, then we start. Then we discuss that by looking at the parameters n, gamma, and mu, we can determine what this basic reproductive number is or not, which indicates how many individuals will an infected person will infect in an otherwise totally susceptible population. And we saw that that number is given by n times n being the number of contacts that are the number of contacts between an infected between infected and susceptible individuals, gamma being the probability that such encounters would lead to an infection event, and mu being the uh, the it's the frequency, or 1 over mu is the time that a person spends in this infectious state. So now when it's been discussed again, we talked about this a little bit last class, or not, it's been discussed in the news nowadays because it's important to determine what the infectivity of the virus is. And we talked about how different variants of SARS-CoV-2 or what the R naught number is for these different variants of the of SARS-CoV-2, namely alpha, which is around, the estimates are it's around 3, and delta, which estimates that around, which is estimated to be around 10 or so, being just as infectious as the chickenpox. So we saw also that there are certain indicators of that when we know what the parameters of the model are, we can determine, there are certain indicators that we can look at that will tell us what the dynamics of the model, or that we can beforehand predict some of the dynamics of the model just based on the values of these parameters. So for example, we can determine when the epidemic will start to decrease, and this is when S is not over, so the fraction of susceptible individuals with respect to the initial population is smaller than 1 over R naught. And that's again, these are important indicators because they tell us when or what the dynamics of the epidemic are. And if we, for example, from a public health policy standpoint, if we knew what the parameters of the model are, and we had some confidence on those parameters, we could anticipate and prepare based on the information that we can get out of the model. So we, for example, we would be able to determine we will beforehand when do we expect the disease or the epidemic to reach its peak and start decreasing. And again, we did mention that this idea of identifying what the peak of a epidemic is going to happen is important, because that is the way we can when and how badly it will be, because in terms of the public resources that would allow us to make important decisions that would help us, for example, based on the decisions that we implement, we could either reach herd immunity more rapidly, or we could flatten the curve, which have slightly different implications, but they will both, for example, decrease the strain that the epidemic is putting in in the public health resources. We did talk about what the effect of some containment measures are and how they could be represented in the model. So, for example, reducing N, which is the contact between susceptible and infected individuals, will require to sort of implement types of lockdowns or other measures that prevent people from getting in contact with each other. The problem about this type of measures is that they are hard to enforce, and they also have pretty damning economical implications. We can also reduce gamma, which is the probability of infection per contact. Right, wearing mask is an example of this type of measures. Of course, there's always a chance that any of these measures could be politicized, but that is independent of the model, right? That what the model tells you is that the rate at which people get infected, it depends on how many contacts there are and the probability of infection per contact. And from that we can readily infer that either reducing the number of contacts or the probability of infection will reduce the rate of transition or the rate of infection. So some of these measures will allow you to either reduce reduce a fraction of the population that is susceptible. Vaccination, for example, does that as well. And the idea is that once we've reached a particular threshold, you reach this herd immunity, which is the idea that there are the susceptible population relative to the recovered population. It's so small that, or the population that's acquired long-lasting immunity, that the probability of encounters it's between susceptible and infected individuals is much smaller. Then another indicator that we looked at from the perspective of the parameters of the SIR model is how to identify the maximum number of infected individuals. And again, the estimates are discussed. How to derive the equations discussed in the references suggested at the beginning of the lecture. But the idea is that if we somehow know what R naught is, we know what the susceptible population is, we can estimate beforehand what the maximum number of infected individuals will be. And again, this is an important indicator. It tells you how many people what is the maximum number of people that will be infected at a single time, and that is critical to know, again, from a public health perspective. Again, I do want to mention this, and this is something that we will come back to later. All of these discussions assume, or all of these estimates assume that you somehow have access or knowledge of what the parameters of the model are. The problem in real life is that we do not have direct access to the parameters of the model. So we have to somehow infer them from the data. And this is what the second part of the lecture is going to be about. So additionally, we looked at how how the some of these important indicators of the epidemic depend um, on the parameters, specifically how do they depend on R naught. And what we looked at is that the number of people that would get infected during the epidemic increases as R naught increases. And basically after R naught reaches 4, basically all of your population get, if you know that your R naught is 0, is 4, you know that basically the whole population will be infected by the end of the epidemic. Of course, this is a mathematical fact that arises from certain of the assumptions of the SIR model. One of the most important assumptions on this type of ODE models is that every individual has possibility to encountering every other individual, and that is, of course, not a realistic assumption, but it's incorporated into the OD models as a simplification, right? So you would expect in real life that if your R naught is around even 4, 5, or 6, you still wouldn't necessarily expect all of your population to be infected at the end of the epidemic. What we saw is that we also saw that around 1, there are big change as we move from 0 to 1. Very small increases on the value of R naught lead to very big increases in the fraction of the population that gets infected. So that is also important, because if you are in a situation where you know that you're because the thing is that R naught is not right, because R naught depends on things. It's not a intrinsic property of the virus, right? It's a because it also includes things that we can or between people. So if you know that you can reduce, you're around 1, you know that any containment measure that slightly decreases R naught will very likely result in big changes in terms of what the outcome of the epidemic is, in terms of how many people gets eventually infected. So if you are in this area, right, I think it's you're in an area where you have where you can maximize the effect of reducing R naught. If you are in this area, there's a lot of effort you have to put into reducing R naught without necessarily gaining a lot of benefit from it, from a benefit from a public health perspective. Lastly, we looked at how the maximum number of infected individuals and the time to that maximum depended on R naught. And we saw that as R naught increases from 1 to 20, your population, the maximum number of the population infected at a single time increases like this saturated function here. When R naught is near 20, almost 80% of the population will be infected at the same time. If your R naught is 10, you can expect that at the peak, at least 70% of your population will be infected at the same time, and so on. If your R naught is 2.5, you can expect that at the peak, 20% of the population will be infected at the same time. And those are important numbers, right? Again, we discussed this last week. You certainly want to be prepared and have the resources to treat as many people as possible. But for example, we currently don't have the resources if, let's say, 80% of the population of the United States was infected at the same time with COVID. So at least it's important for us to know from a public health perspective, what should we expect given what we know about the transmissibility of the virus. And again, the time that it takes to reach that R naught is also important, because it sort of like gives you how much time you need or how much time you have to, let's say, if the pandemic started, if an epidemic started, how much time you have to, let's say, prepare to reach the peak of the epidemic. And the smaller R naught, the more time that it takes to reach that peak. Finally, we ended up last class talking about the fact that in reality, what we have access to most of the time from it's the epidemiological data that we do not know beforehand what the parameters of the model are, but we do have access to some data that can possibly reflect the dynamics of the model, and that if we look at that data and we assume that the data behaves as an SIR model, then we can estimate what the parameters of the model are from just this data. So the previous part of the class, we were estimating all of these important indicators of the epidemic from a prior knowledge of what the parameters are. But again, in reality, we do not know what the parameters are, and then we need to somehow estimate them from the data. Okay. Before going into this exercise, is there any question about what we've discussed so far? If not, then I'll start, because all of this was up to here was basically a recap of what we talked about last week. This we did in class too, but I'll do again because it's connected to what we do in the latest parts. So any questions before I move on? Okay. Cool. So okay. So if we want to be able to estimate the so the active cases data or the infectious data, pretty much it's gonna closely resemble your, or if your infectious active cases that are closely resembles your infected curve, we can use the shape of that curve to estimate the parameters of the SIR model, and that's all we need. The first part is to use the trailing end of the active cases data to estimate the parameter mu. And the reason is because we assume that in this part of the in this trailing part of the curve, the rate of new infections is small, because the number of remaining susceptible individuals is small. So we can, given that we make that assumption, then the rate of change of the infectious curve, which is this one, is given only by minus mu times I. And then if we integrate this differential equation, we get this solution. And using this solution, because we know, so for example, if we pick an original, we pick a, let's say, high part in the upside curve, in the downside curve, and then we pick another point, and we look at the slope, then that slope is supposed to give us what the value of mu is. And that's what we did in exercise 5.1. And I'll do it again. We'll do it together again, just to recap how we did it last time and what the estimates are. Just 1 second. Okay. 1 second. Yeah, again, I've uploaded all of these class exercises into the Google Drive lecture 5 demos. These are the same last week. They're just renamed for your convenience. But you can, I'm gonna again share the poll just to make sure that everyone is able to have access to the files and upload them into NanoHub or launching launching the Jupyter Notebook locally if you have Tellurium installed. Please do let me know that you've been able to upload and have access to the notebook by hitting finish with exercise in the poll. Giving everyone a couple of more minutes. I'm waiting on just one person, so I want everyone to at least have access to this. Okay. Oh, sorry. Okay. Okay, everyone. So it seems like everyone had access to the file. So in this exercise, what we're doing in this first part is that we are basically generating our data, an active cases data from the SIR model. So again, in real life, we don't know what the parameters of the model are, but in this exercise, what we do is that we sort of like generate the data ourselves. So we know what the ground truth is because we set the parameters of the model. But in the remaining parts of the exercise, we're going to assume that we do not know what the parameters of the model are, namely S naught, mu, and n times gamma. And we will infer try to infer these values from the active cases curve, right? And again, the active cases, we assume the active cases curve corresponds to the infectious curve in the SIR model. So in this first part, as I mentioned, we can use the assumption that in the trailing curve of the of the infectious or the active cases data, the rate of infections is small, or the rate of new infections is small, and that such that we can estimate the value of mu just from the slope of this curve. And to do that, we have to choose at least two points in this curve. And when we plot it in a semi-log scale, this line has to look linear. If this curve does not look linear, then your approximation or your assumption that the rate of new infections is small is not is not justified, and you will have to look at a different, let's say, at a later point in the trailing part of the curve. So using this slope, we estimated what mu is by, let's say, choosing a point on the higher part of the curve. Let's say at time 10, the value of the curve is 10 to the 1.9. At 18, the value of the curve is 0.2, 10 to the 0.2. We plugged in those values into this formula, which is what we get by solving this equation. And we get what the value of mu is. And the value of mu is from this estimate, it's 0.48. And remember, our ground truth was, we said, when we generate this data, we set mu to 0.5. So our estimate, even when it's a rough approximation, is actually a pretty good approximation. And I wanted, again, I want other people to do this exercise here, but choose different time points. Let's say choose 12 and 16, and please do write in the chat what values of mu you're getting. You can choose whatever times you want other than 10 and 18. Just report what times you chose. You can do it in the chat, and what values of what times you chose. What were the times of the curve that you assume by reading the curve, by reading the plot, and what the value of mu is that you're getting. I'm going to launch the poll again to give people time to do it. So again, the exercise is pick different times other than 10 and 18. Look at the values of the curve, plug them into this equation, and tell me what values of mu are you getting. And you can tell me in the chat. Okay, cool. So while you guys work on this, just notice that I've trimmed the part of the curve. I've trimmed the plot so I can focus on the part of the curve that looks as a straight line, as a decaying straight line, to sort of like estimate what the parameters are from there. But if we look at the curve itself on this log scale, so we see how the complete curve looks like. And so we know, for example, that anytime after 8 is good. Anytime after 7.5, it starts already looking a little bit less as a straight line. If we do 6, definitely here, the approximation is not as good. If we do 5, clearly we're outside of the zone. So we cannot use at time 5, or let's say 5 days, because it's already, we're not yet at the trailing end, at the trailing edge, at the trailing tail of the curve. Okay. So once we've estimated mu, we can use the leading part of the curve to estimate n times gamma. And notice that it's that we cannot independently estimate n times gamma from this data. We would need additional data to be able to do that. We can estimate the product of n times gamma, which is often called beta. This is the infectivity parameter. And the way we do that is, again, by assuming that in this part of the curve, at least on the very early part of the curve, the number of infected individuals is small, such that the fraction of infected individuals, right? So so that the number of individuals is small, so the fraction of the total population that is still susceptible is It's almost 1. I'm missing here the fraction. But by assuming that this fraction is 1, we can then solve this equation. And then by solving this equation, we can then use, let me fix this because there's a typo, and I did say I would fix it last time and I didn't. We can use the slope at the beginning of the we can use the slope on the upside or the leading end, and we can use our estimated value of mu to then estimate what the product n times gamma is. Again, notice that if you have no idea of what mu is, and you only have this trailing end, or this leading end, you cannot still estimate what the parameters of the SIR model are. And that complicates things from a public health perspective, because you sort of like have to wait until the peak of the epidemic has passed to be able to estimate the parameters of the model. There's no way you can estimate just from the leading edge all of the parameters of the model. But again, the idea is now if we look at the leading edge, at the leading tail or the leading part of the curve, we can use that slope to estimate what n times gamma is if we know what the value of mu is. And this is the second part of this exercise. It's in the same notebook. What I'll do is that I want, because you already know what the formula is, we already have an estimate of mu that is 0.49 or 0.4889. I want people to, using this plot, plug in values in there and that are not the ones I used here. I use times 1.8, I use times 3 and 1.5. Use different value times and try to estimate what the n times gamma is. And please do put it in the chat as well. And do tell me at least what times you use to estimate the slope of the curve. So Benjamin, you used 5, so it means that you increase the range over which you were looking at the curve. Because again, in this case, you also need the curve to look like a straight line to be able to estimate the slope and for your assumption that you're in the leading part of the curve to be correct. So if you use 5, you're already at a point where the curve is diverging from that straight line, which means that your assumption that the population is still relatively susceptible might not be a correct assumption. So in this particular case, I would use any time from 0 to 3, yeah, 0 to 3. Okay, yeah, so that's fine, right? Because yeah, that's the point, right? If you choose numbers or outside of the range, yeah, you would expect your estimate of beta to be incorrect because again, your assumption that we are in the leading part of the curve is incorrect. Yeah, that's a good point. Good. So now that we've looked at the leading part of the curve and using our previously determined value of mu, we can also get an estimate of what the value of beta is, or n times gamma is. Once we know n times gamma, we can use this information to estimate what, and again, we know what, we know the ground truth because we put it ourselves. So beta in the ground truth is that it's 2. In our estimates, we might be a little bit off because we are doing this, we are basically eyeballing it. So there might be some measurement errors, but we're all within a reasonable range. And remember also that any error that we get in mu propagates then to our estimate on beta, in beta. But the idea is that now that we know what beta and mu are, then we can use our this information to estimate what R naught is, and that is beta over mu. In my case, given my estimates is 3.5, which is close to 4, which is the actual ground truth value, right? Beta over mu. And then if I look at the maximum number in the active cases, which is around 400, then I can plug that information in this formula that we looked at before, right? That allowed us, if we know what the initial susceptible population is, and we know what R naught is, we can estimate what the maximum number of infected individuals will be at the same time. But usually we know, what we know is we actually have access to what the number of maximum number of individuals infected us at a time was. So we can use backwards, we can go backwards to estimate what the initial susceptible population would be in the SIR model, the SIR model that described this epidemic using this formula. So once we know R naught, then we can estimate what the S naught of the SIR corresponding SIR model would be. And we know, we also know what the ground truth for S naught was because we put it ourselves. It was 8,000, and in my estimate is 1,131. Okay, I want to give everyone to run this exercise. It's just running this additional, but give you a little bit of time to, like, given that some of you have different estimates, to run this and tell me, given the values that you were getting in the previous parts, what your new values of R naught and S naught are. Right. Well, Ryan, make sure to run it again because you have a different value of beta than the one I used here. So you should expect to get a slightly different values of R naught and S naught. Right, there you go. So see, even slight differences in these estimates can result in widely different estimates of the values of estimated values of R naught and S naught. Okay. So I just wanted to show you that we've developed a tool that walks you through these same ideas. It requires a little bit less work because it allows users to everything users have to do is to choose the time points where the curves are where the different parts of the curve look linear, either at the trailing end or at the beginning. It's if in NanoHub you can type COVID-19 R naught estimator, and it will, if you're logged in into NanoHub, it will take you into this application. Again, it talks a little bit of the ideas that we've talked about here in class, explains what the SIR model is and what the equations describing the SIR model are, what the parameters mean. It tells you how to use the application and notice that in this application, the data that it's used is actual data from the first wave of the COVID-19 pandemic. So notice it was around 150 days in to the pandemic. So it was pretty early. But it allows users to choose different data sets for New Zealand, Italy, and Spain. And then users can use any of these data sets to estimate some of the parameters of the or estimate R naught based on this based on these same ideas that we were discussing before. In this case, I'm just gonna use the New Zealand data. So the first, of course, as we discussed, if we want to calculate mu, the first, we need to choose the part of that looks like a decrease line with times at which we want to estimate that data. So that's all the user has to do, is to choose the times. And once they choose the time, so basically the idea is choose a time that where the curve looks like a decreasing straight line. Once you do that, you can hit calculate mu, and it will tell you, show you what the it would basically draw a straight line that you can use to compare as a comparison to see how good your approximation was. And then it tells you what the value of mu and the direction of the infection, which is 1 over mu, is for that particular data. Then you do the opposite. You have to choose a part of the curve that looks like a leading or increasing straight line. Still not that good there. And then I can use that part of the curve to calculate beta. Tells me what beta is. Then once I have those two values, I can calculate what R naught and S naught are. And for this particular data set, R naught turn out to be around 5.17, which is actually not that terribly far away from the 3 to 6 estimate that it was for the alpha variant of SARS-CoV-2. Then we can simulate the model and look. This will come back to it, but we can simulate the model and look how far or close we are from the data. James, we never actually tried to, because what we're seeing here is a difference in terms of all this data that was collected when there were basically no infections.
Right, the zero time is very sensitive because it takes a long time to take off. So
right. So what we should actually do is probably eliminate some of this data where there were basically no infections whatsoever, but they were being recorded, because at least in New Zealand started much later. So they were already recording data when there were no cases. But there was basically no epidemic happening or a pandemic that has hit at New Zealand at that time. So we need to fix that.
you have to fit it when the number of cases is 100 or something like that to line it up. Yeah.
Right. So I'm gonna give people, the next part of this application is what we discuss in the next part of the class. I'm gonna give people a little bit of time to play with this application. Please do hit finish with exercise when you're done running it, and I will take I know it's early, but I need a 5-minute break to drink some water, and I'll be back.
If there are any questions now, we can. Are people able to keep up with the exercises? Okay. Fitting is a bit of an art. It's not, I mean, there's lots of mathematics around it, but ultimately every problem you fit is slightly different. So one has to be willing to play and poke at it a little bit to get it to work. I mean, one lesson of what you're seeing here is that the SIR model is a lot better than an SI model or an exponential model, but it's still not a perfect description of what's happening. And there's still, I know some people had, for their projects or for the suggestions for papers to potentially reproduce, some people had come up with, found some papers that are trying to estimate these numbers in a more sophisticated way. It's quite complicated because the way infections spread is spatial. If I'm sitting here in Bloomington, I'm not going to infect somebody in New York. And so to assume that the population is well mixed over the entire population of a country isn't really reasonable. And including those kind of spatial effects that you can only infect people near you in a model that's not so easy. One way to do it is to say that the susceptible population increases in time. But exactly how it does is not trivial. And I know some people in class have come up with some models that try to include spatial effects for the epidemic. And those are very useful and interesting. Unfortunately, they're not models that we can run using the technologies we're learning this semester. So if people are interested in doing spatial modeling, it's a great thing. But we have some limitations on what we can do this time.
Okay, I'm back, everyone. Sorry about that. So it's just a little bit humid here, so I was dehydrated.
Your sound isn't working, Josh.
It's not working. Hello, do you guys hear me now?
There you go. That's
okay. Yeah. So as I said, I was dehydrated. I'm sorry about that. I hope everyone had time to play with the tool. Again, the ideas implemented in this tool are the same ideas that we've been discussing the last two classes. You can give it a try using different data sets. And also, as we mentioned, if you go look at the current let's do it together. If we look at the current COVID data, let's say in the United States, you'll see that the active cases curve doesn't necessarily fit that well with the SIR model, what the SIR model curve looks like. But you can still use, let's say, a single a single wave, and assume that each single wave is its own independent epidemic, and then try to infer what some of the parameters of a SIR model are. But again, remember that that is because you're assuming, when you're doing that, you're assuming that each wave it's its own independent epidemic, because you're assuming that previous infections are providing long-lasting immunity, and that all of your population and the epidemic swept through all the possible all of your possible population. In reality, there are seasonal effects associated with uh, uh, with endemic diseases, but also with ongoing epidemics. Some of these waves do reflect changes in public policy decisions as well. So, so they might not be entirely seasonal. They also reflect some of our decisions in terms of what containment measures are being implemented. So, do you guys sort of like can a good guess of when did this last when this last wave started? What type of measures were taken by then to try to curve the current wave? Right, the current wave is mostly due to the fact that the Delta variant is much more transmissible than the previous versions of the previous variants of SARS-CoV-2. But there was an important change in public policy taking around this time that was intended to, right? Well, I mean, they were encouraging vaccination, right? That's when the peak of the vaccination efforts started. But that's also around the time that the I think it was the CDC, or yeah, it was the CDC, would change their recommendations about people wearing vaccinated individuals having to wear masks inside. Remember, they at some point, because we were reaching higher levels of vaccination, the CDC suggested that individuals who were fully vaccinated did not have to wear masks inside. But as cases start to rise because of the increased transmissibility of the Delta variant, the CDC changed the recommendation also around this time.
Yeah, that was an unfortunate recommendation given what happened.
Right. It was probably what is recognized as a very premature recommendation. So again, we could potentially look at every one of these waves and try to use it as its own independent epidemic to try to estimate, okay, what was R naught during this phase, what was R naught within this phase. It's much harder to use even a model that can give you some oscillatory behavior. It's much harder to model a full epidemic, a full pandemic like the one we are experiencing now, just with very simple models, such as the models that we're looking here. So that type of modeling will require much more complicated formula, much more mathematical formulations of the model, and also additional assumptions and model structure in terms of having influx of people and so on. There's a couple of, I'm not necessarily sure if we're intending to replicate some of the papers as we did last year, but some of these papers do looked at how to model seasonality, for example, of certain diseases. So that would be interesting.
Right. Well, one of the reasons we did the homework problem with the SIRS model is because it shows the waves.
Right.
They're not the shape that you get here, and the amplitudes won't be quite right, but it does give you at least the simplest model that'll give you the successive waves of infection.
Mhm. Right. Okay, so just one second. I'm gonna stop sharing my whole screen, and I'll come back to the presentation. Okay, so as I mentioned in most of the preceding parts, we assumed that we had, when we were estimating important indicators of the pandemic, we assumed that we had prior knowledge of what the parameters describing that pandemic would be. In reality, we do not have access to those parameters, and we have to infer them from the data. One way is to do it the way we did, by actually by measuring the curve, the different parts of the curve, and try to estimate what the values are. But let's say you have incomplete data. Let's say you want to estimate what the parameters of the model would be at the beginning of the epidemic. Then you would have incomplete data, but you could still use certain fitting algorithms that you could use to fit the data to, and try to estimate the parameters of the model. James, and actually we haven't done that, and that's probably something we can do together in class. We could potentially cut off the synthetic data to just the beginning of the curve and try to use the fitting to see how well we can estimate the parameters just from that part of the data. That would be an interesting exercise. We can probably do it. We can do it together today. But before going into the exercise, we wanted to go back to because some of you have already have experience with optimization and probably parameter fitting as well. But for those of you who doesn't necessarily have this experience before, we wanted to fall back into the basics here and explain what the principles and the objectives of optimization and parameter fitting are. And again, the idea of parameter fitting is that you have some experimental data of interest, and you have a model that you think describes properly the mechanics of the infection, right? How is infection being propagated in your how is infection propagating in your population? And you say, okay, I think it is an SIR model is a right way of thinking about what the experimental data that we're seeing. But you have the model and you have the experimental data, but you need to estimate what the parameters of the model is from that data. And once you make, which will make your model predictions, right, agree with the experimental data. And that's the whole purpose of the fitting process. The fitting process is the idea that you want to make your model predictions agree with the experimental of the observed data. So and then once you fit it, your model to the data, there's also the questions about you can make yourself about what is your confidence in those values that you've estimated. How good is this parameter? Is a model at all? Or whether, let's say, your data is noisy, and whether it allows you to have some confidence on the values that you've estimated. And that's something that will probably come back to. Those ideas are probably ideas that we will come back to later. But for the fitting part, you certainly need to have a model that that sort of explains what the data is. You have to have the data, and you also have to make a decision. So sometimes, in these models are quite straightforward. Sometimes you have very complicated models fitting all of those parameters becomes extremely complicated, and sometimes you, depending on the model and the data that you have, you might have prior knowledge of prior and independent knowledge of what the some of the values of these parameters are, and you might be able to let's say fix those values and then use the data to estimate the values that you don't know. You need a way to quantify how far your model prediction is from the experimental data, and you need to specify what is your tolerance, how much distance you're going to tolerate between your model predictions and your data. So those are the basic, let's say, the basic components that you need in order to be able to fit the model to the data. Then once you've made those decisions, then you use a numerical optimizer that is going to do the fitting for you. And the idea of the numerical optimizers is that they generate series of parameter values, and for each of them, for each of these sets of parameter values, they compute the distance between the between the model prediction and the experimental data, and uses an algorithm to generate, based on that information, uses an algorithm to decide a new set of parameter values, and then eventually returns a parameter, a set of parameter values that minimize the distance between your model and the data, or where the error, what we call the error, is smaller than the tolerance level that you are willing to, or the distance that you're willing to tolerate. These numerical optimizers follow different strategies. We'll see some of them today. Some of them are deterministic versus stochastic. Some of them are sequential versus parallel, and some of them do local versus global searches. And we will see examples of some of these strategies in the next couple of slides. So the most basic idea is, or the most basic or as from the modeler's perspective, the most important thing that we have to do is to be able to quantify what the distance between our model and the data is. And in this particular example, let's suppose that the data that we have access to, which is not usually the case, but let's suppose that we have access to the data, a data where the susceptible population is decaying exponentially. So we assume that our data looks like this. So we assume that a model where our susceptible population decays exponentially is a good way of describing this data. So the way we specify that model would be in this form, or we can write it as a differential equation. Let's see if I can draw here. The SDT equals minus K1 times S. So what we want to do is to use this experimental data to determine what the value of the parameter K1 is. And notice that for a specific value of K1, the model will have a prediction. Well, it will predict that the population will decay following this dynamics, right? And now we see that they are not exactly the same as the experimental data. So we can quantify what the distance is between our model prediction and the experimental data by basically measuring the distance between the model prediction and the experimental data. So that's our way, the way we can quantify that distance, right? We look at or quantify how far away our model prediction is from the data is by looking at the distance between the model prediction and the experimental data. And we call this distance the residuals. That's an important concept because that term is gonna come, we're gonna keep referring to this concept. And again, the residuals refer to what the difference between the model prediction and the data is at a single time point, right? So for each single time point, we have a different residual that we quantify as the distance between model prediction and the data. And then notice that if we had different values of K1, then those different values of K1 will have different model predictions. And for these model predictions, each different model prediction, let's say this is K1, a K1 value of K0.25, and this is a K1, and this is a K1 equals 2. So for each these different values, we have a different residuals or different distance between the model prediction and the observed data, right? So this introduces the idea that there is a value of K1, which will somehow minimize the distance between the experimental data and the model prediction. Okay. And again, I'm gonna launch the poll. Let me see, there's a poll that should, because I want to make sure whether I have to repeat this because this idea is so important that everything that we will see after is based on this notion, the notion that there is a parameter value or there's a set of parameter values that minimize the distance between the model and the data. So James, is there a poll where I can ask if I need to repeat or go over this idea again?
I'm sorry, I don't have one set up, but you could use that poll you have by saying, if you want me to go over it again, click need more time or
need help.
Need help.
Right. Okay. This one. Okay, so it seems like, it seems like we're good. So again, the reason I'm launching this poll is because this idea here is so important that we need it to have at least a decent understanding of it to be able to continue with the next ideas in the lecture. Okay, so although there are multiple ways in which we can quantify the difference, that the typical way of or the golden standard to quantify the difference between model and experimental data using a single number, it's what it's called chi-squared. And chi-squared, but basically is the difference between the data point and the model prediction for that single parameter value. And then you square that difference and you add it for every single point. So basically, again, here, we will take this difference, which is around 2, well, 8 minus 6, which is 2. We would square that, and then we add to this one, which is 4 minus 2.5. We square that, and we add it, and then we do that. We do the same for every single point, and then that number that you get from calculating the distance that way, it's what's called chi-squared. And then chi-squared is, of course, a function of remember that every single value of we are representing what the difference of the model for a parameter value is with a single number. So for different values of that parameter, you would expect chi-squared to give you a different number. So you can think of chi-squared as a function of the parameter values, right? And that's why it's called the objective function. If you think of it as a, let's say a two, in that previous example, it was just a single parameter, but if you think of it as a 2-parameter optimization problem, then you can think of that objective function as a sort of like a 2-dimensional landscape. And again, the idea of the optimize, right? So each point in this 2-dimensional landscape is a different combination of the 2-parameter values. And in this particular part of the landscape, the difference between the model and the data is the biggest, whereas in this valley, the difference between the model and the data is at a minimum, right? So what you want your optimizer to do is to intelligently explore, and that part is important because it's not a random search, right? It's an intelligent search of the this landscape to be able to somehow get what the parameter values are that minimize the difference between your model and your data. Okay. So different optimization algorithms work differently, but all of them have certain common principles. They work following they sort of like follow this routine where you start with an initial guess of the parameter value. So you choose, let's say, a point in this landscape. Then the optimizer will compute what the landscape, what the value of this objective function is. And then it would generate a new set of parameter values based on the information about the landscape, trying to move towards regions in the landscape where the difference is minimum. and then again, the idea is that the optimizer generates these parameter values, evaluates what the cost function is. The cost function returns, or once it's evaluated, it informs the optimizer such that the optimizer can intelligently generate new sets of parameter values so it can somehow move around this landscape. And we'll have a video, and you're right, James, that video that showed the simulating and annealing was a good video to put in here. But we'll come back to that later during the lecture. Before you run the optimizer, and this is something we run frequently into in actual research, there's plenty of problems that you can run into when running this optimizer. Some are more obvious, some of them are a little bit more subtle. So that's why James was sort of mentioned last time that optimization is a mix of a science and an art. You sort of, as you do it, you sort of get certain intuitions about what type of strategies work the best. But some of the problems that you might run into is that your initial guess of parameter values is they are bad in the sense that they are too far away from the minimum, and your optimization algorithm is unable to find that minimum because of the type of initial guess that you had. There's also a problem of the range in which you want this parameter to, in which you want your optimization to explore the landscape, right? Because if I restrict my optimization, my optimizer to look into this part of the space, it won't definitely find a good solution or a good fit of the model to the data, right? So I have the range of that I'm allowing the optimizer to explore has to somehow include the minimum in there without you actually knowing that the minimum is in there. So that's a little bit of the guesses that you have to make. There are some strategies around that. You can so for example, you can start running your optimizer over very wide ranges and then do some sort of like logarithmic search, and that allows you to jump like make like bigger jumps in the parameter space. And then once you get a sense of what the landscape starts looking like, then you can probably narrow those ranges. When you're dealing with biological data, some of those ranges are biologically constrained. So for example, one of the parameters that I'm trying to estimate in my research now is how long does it take for cells to start producing RSV, which is a respiratory virus, and a respiratory syncytial virus. So that number is not readily known, but you would expect RSV to start producing virus anytime between 4 hours to 2 days. So when you run your optimizer, you can sort of like constrain your model such that the range it looks for that parameter is within biologically realistic numbers. And there's also the problem that there might be certain trade-off between your parameters. So as we saw from the data that we were looking at, we were not able to estimate independently what n times gamma is. So if I define n times gamma as two different parameters that I'm trying to estimate, there is always going to be a trade-off between those parameters because my optimizer can decrease n, but the same amount it increases gamma, and those are still equally good solutions. So those are the type of some of the type of problems that you can run into and that it does require that you acquire by sort of like getting some familiarity and developing some intuitions about these algorithms. There's also other types of problems that your optimizer can have. In the best case scenario, you want your optimizer to go straight down, let's say the valley until it reaches the minima. But sometimes your optimizer can get stuck in what is called a local minimum, which is a region of the space that it's sort of like decreases the difference, but it's not the best solution, the best possible solution. Another one, and I talked about this one, is that you get, if you're too far away from the global minimum or the minima, you might be stuck in a region where it's a neutral area where there are basically no differences. No matter what parameter values you try, there's basically no difference in the optimizer is unable to minimize the distance between the model and the data. Another very common problem is the overshoot. That's what we call how is it that we call it, James? Golf hole problems.
Yes, exactly.
Right. So your minima, basically, the gradient of your near your minima is so steep that there is always the danger of your optimizer overlooking it, because the step it takes, it's so big that it sort of like misses where the minima is. And that is actually a very, 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 very common problem with when that we run into when we're trying to fit models to actual biological data. Okay, so I want to spend a little bit of time discussing what some of these optimization algorithms or how some of these optimization algorithms work. We're not going to go into a lot of detail. Herbert's chapter 6 goes into a lot of detail explaining how these algorithms work. We're just going to present the ideas here just to see, just to get a sense of how these algorithms are working. If you want more detail, I would refer you back to Herbert's chapter, which is actually quite good. One of the most common optimization. Oh, okay. So before, the first couple of optimization algorithms that we will be looking at are what is called local optimizers or local fitting algorithms, and they are local in the sense that they don't usually explore wide ranges of the parameter space. They sort of assume that you already are nearby a minima when you start running, or that you have already a pretty good guess of what the actual ground truth value of the parameters are. And all you need is to, let's say, refine those estimates. And that is, for example, the case in the previous exercises that we had, where we saw that although we did not have the exact ground truth value, we already have pretty good estimates of the parameters because we were able to estimate them from the data. So in those cases, you want to use some of these local optimization algorithms. They have the advantage that they're usually quite fast and less computationally expensive. But again, if you're not close enough to the best solution, you might run into problems and you might not get reliable results. So one of the most common algorithm it's called gradient descent. And let's assume that we have a one-dimensional parameter space, right? So the parameter space looks just like this. So if we are, because we are already nearby the minima, the way the algorithm works is that you choose a starting initial point along this curve. And then the algorithm is going to calculate the slope at that part of the curve. And once they've calculated the curve, it's going to choose a new point down that curve that is given, is control using a step size that is controlled by this parameter alpha. It's proportional to how steep the curve is at that point. So how far you move down, it depends on again, this alpha parameter that is mostly internal to the optimizer and what the gradient is at that point. And of course, the gradient, it is not guaranteed to move always, let's say, on the same side of the curve, but it will always try to move down, down the slope. And then the process is repeated until, again, the gradient is below a certain threshold, which is probably which is the tolerance or the error that it's the optimizer is willing to accept, right? So in this particular, this is actually me implementing gradient descent, and you can see how given the value of the parameter alpha that I chose, how many steps it takes for this optimizer to run to find the global minimum. So again, it's always what the step point is. It's always proportional to what the slope is at that particular point. So that's why it's called gradient descent. Another log optimization algorithm is Levenberg-Marquardt. It's basically a sophisticated version of the gradient descent. And in this particular case, it's when the gradient is steeper, it uses the gradient descent, but near the minima, where the region tends to flat out, uses a quadratic approximation. So instead of moving on a straight line, it moves more like on a parabolic way. And it's supposed to be more efficient and more sophisticated than the gradient method, because it approximates when as you get closer to the minima, the curve starts to flatten out. So instead of moving or the parameter space, the objective function flattens out. So instead of moving in a straight line, which usually makes you overshoot, then you move a little bit on a quadratic approximation. A more sophisticated and actually robust local optimization algorithm is what is called the simplex method, or Nulder-Mead. This is actually quite common algorithm used in research, and this is an example of how the algorithm works. The idea is that it relies on this mathematical construct, which is a simplex. And the simplex is, the way it works is that it chooses 3 points in the parameter space. And based on information on these 3 points, it determines how to move. It sort of makes the simplex evolve in such a way that at some point it reaches the minimum. And you can see an example. So assume that this contour plot, what's happening is that this is basically the minimum point down here. And this is indicating that you're going up and up the gradient. So the simplex method will sort of like generate new simplex until it's able to find the minima in the parameter space. But again, this is also a local optimization algorithm. So it's not intended to explore the parameter space much more thoroughly. So again, it's a good algorithm to use when you know that you have a good estimate of what the parameter values are. So, all right, this is the same ideas I was talking about earlier. So this is how roughly the simplex method works. It starts with three. Let's suppose that this lays on top of the parameter space. It starts with choosing 3 points in 3 initial guesses in the parameter space. And then once you've chosen these 3 points, it calculates what this centroid is. Then it identifies the worst point in the simplex and reflects that worst point across the centroid. And then if that reflection is better, then it expands the simplex in the direction of the reflection. If the reflection is worse, it contracts the worst point in the direction of the centroid. And if that construction is worse, then it contracts the simplex towards the best of the points in the simplex. So it's basically calculating what the shape is. It's basically using a 3-point sort of reflection and construction to determine what the value of the objective function is, and trying to find the minimum. Okay. Again, I'm going over these ideas relatively quickly because I wanted to give you an idea of what the different strategies are that these optimization algorithms use. But if you want more detail, again, I will refer you to Herbert's chapter 6. He goes into a lot of detail explaining some of these. When you don't have a good estimate, or you have no idea, no way of knowing what some of the values of your parameters are, you can use these global optimization algorithms that will allow you to explore the space more thoroughly. And the advantages of these global optimization algorithms is that they are designed to avoid local minima, right? Because in the local optimization algorithms, you assume that you are already nearby the best solution. But in reality, you don't know, you might not know. So you need your algorithm to be able to get out of local minima and continue searching the space until they find the global minimum. And that's why they're called global optimization algorithms. And here is an example of how the simulating annealing works. In simulating annealing, and we will discuss it later, but how fast and this searching algorithm works, it depends on a mathematical term called temperature. And as you can see that as the temperature cools off, the algorithm jumps moves less and less inside the parameter space, and eventually converges to this minimum in the space here. So again, I'm going to run it. At the beginning, the temperature is very high. So even though it actually got into the minimum, it moved away because the temperature is still too high, and it allows the optimizer to jump away from the minima, just to make sure that it's not getting stuck at a, let's say, at a local minima. But as the temperature cools off, the algorithm settles and converges into the global minimum. Okay. So again, the idea here is that you start with an initial guess, and then another point is randomly chosen, and based on the temperature and what the value of that of the landscape is at that point, the algorithm makes a decision whether to either move down or move up, right? And that's basically the main difference between global and local optimizers. The local optimizer, if you start here, will start to move in this direction until it reaches this minimum, right? And then that's the difference. That is the parameter value that it is going to return. But that is not the global minimum. So you need your optimizer to be able to move upwards, up the gradient, to be able to get out of these regions that are local minima, and eventually get to the global minimum of the landscape. And again, the probability in the simulated annealing, the probability that your searching algorithm is going to jump away from a local minima is going to depend on the temperature. If the temperature is high, your probability of moving away from local minima is higher. If the temperature is small, then you basically move down the gradient. For the annealing algorithm, this temperature decreases according to what it's called an annealing schedule that often has to be specified by the user. And that part is important because if you do not choose the correct annealing algorithm, then you're basically cooling off your system too fast and not allowing your algorithm to find the global minima. Or if you cool it off too slow, your algorithm might have convergence errors and might also get stuck at different local minimums. The last one, I'm not going to go into a lot of detail, but this is also a very common algorithm, is the genetic algorithm. Here, ideas of biology are used to generate a population, which is a set of points in the parameter space. And each of these had a set of genes, which corresponds to the parameter values. And then these parameter values give each member in the population a specific fitness, which is the value of the objective function where the individual is located, and then using ideas such as mutation, selection, and crossover, the algorithm can make the population evolve such that the new individuals are chosen that increase the fitness with increased fitness, which corresponds to higher points in the or in this case higher, but you can flip it around, lower points in the parameter landscape. So yeah, you flip it. We've been always talking about minimizing because we're talking about minimizing the difference between the model and the data. Is a natural way of thinking about it in terms of finding the minimums. But if you flip it around, then the problem is how to find the maximum, which is basically equivalent. Again, as I mentioned, the genetic, I'm not gonna go into the detail, but the genetic algorithm uses these ideas from natural evolution as selection, crossover, and mutation, and basically generates different populations with the idea that each iteration or each generation increases your likeliness that one of the individuals is found at the maximum of the or the minimum of the parameter space. Okay. So I'm gonna stop here now. I'm gonna take another 5 minutes break. I'm gonna take 5 to 10 minutes break. I want everyone to be able to load the next part of the exercises into NanoHub and or locally, and we will continue. We won't actually discuss more about the algorithms themselves. We will assume that we know what they do when we call them. But what we'll show next is how this all can be put together so that we can actually we can combine Tellurium with available libraries for optimization, and then we can combine those to fit the Tellurium models to, let's say, available data that we would have.
So this is
okay, so fine. So what were the equations given in the homework?
Oh, I can just share the whole thing then. This one.
Okay, so you have correctly identified that there is a typo in the homework. Which is that the rate at which you recover. Let's ask you a different question. Do the equation as given in that homework problem make sense?
Not really.
Right. So based on what we've done in class so far, what do you think is possibly wrong with what is written there? I will go fix the homework. This is the problem with editing a homework assignment at the last when it's underway. So ask the question when you look at a model, and this is not something that people know. I mean, this is not something that I expect people to be able to do instantly at all. You have to ask the question, does the model behave in a way that would make sense? And you have absolutely correctly typed what was written in that homework problem. And you have identified that there is in fact a typo in the homework problem. And I'm looking for the text version of that problem so that we can fix it. Does anybody else in the class see what the mistake in the assignment is? Because there is in fact a mistake in the assignment, which you caught. So,
I mean, from looking at the graph, it looks like the recovered individuals don't go back into the susceptible. It just doesn't account for them being back in that population.
Okay. So does it make sense that the rate of recovery would depend on the number of infected people?
No.
shouldn't the rate of recovery depend on the number of people who are, let's say the rate at which you go from recovered to infect back to susceptible, shouldn't that depend on the number of recovered people? Yeah. So that should be R rather than S. There you go.
Awesome.
So now try that. It changed that one character in your, let's see what happens. There you go.
Cool.
Now it's working. Now, one thing that I would do is you've only got 10 points. Yeah, I would interpolate. There you go. And now you've got
That
the
looks
waves
better.
of infection.
That looks better.
And I apologize to everybody for that. Did other people get stuck with that?
Oh, I was looking at that for a while.
No. Well, I appreciate your bringing it up. Did anybody else have the same problem? Okay, well, thank you. So please feel free to reach out. If you're, my typical assumption is that people work on these homeworks during the weekend, which is why I hurried a little bit to try to get the revised homework out, because I realized that the homework we originally assigned assumed the things that Josh was covering today. And so I didn't want people to get stuck on that. And this was a problem we were originally going to assign this week. And then, but we thought it would be possible. So unfortunately, when I copied the problem in, I managed to introduce that error. So I hope that did everybody catch what the correction was? That the rate of recovery of going from recovered to susceptible has to be proportional to the number of recovers. Great. So people should just, when that kind of thing happens, if you let me know, I'll do my best to let everybody know. So because if one person's stuck, probably everybody's stuck. But also I will do my best to clearly, if there's a problem like that, we'll hold the problem assignment till the next week. So I really appreciate your catching that. And I think that the problem should be addressable now. This came up really because we wanted to see whether you could get an approximate estimate of the how much of a problem the Delta variant was. And you'll find out using the numbers from the fits that we've done in class that the Delta variant really is a big problem. I mean, without the vaccination, it's really a serious issue. The other thing that's, I think, is nice, which you, from what you were just showing, if you could from the screen share, which you just showed, is that you get the waves of oscillate of the infection, and that's the key thing when you include that SIRS model. You could get these waves of infection, and it's sort of interesting to look at what controls the period of those waves. In reality, for COVID, they're about 4 months. And that tells us something about the way that the disease works. Josh, are you back?
Yeah, I'm here.
Okay, great. So did you? I don't know where you came in on that, but if you want to take over.
I was here.
That's great. Okay. Thank you very much. I really appreciate Delaney for your catching that.
Yeah, good. So yeah, and like I think it's useful to go over homework assignments if people have questions. I think it's useful. Let me actually stop sharing my full screen now because the next exercise will require the code.
Sorry, you probably want to adjust your mic. You're a little faint.
What about now? Do you hear me? Do you hear
That's
me
good.
better?
That's perfect.
Okay. Okay. So in this second part, we'll come now. We will refer to exercise 5.2, and again, the first part that I should have this the relation between the optimizer and the cost function back here again. But the idea is that now we need to somehow connect the optimizer with our tellurium simulations and the data to be able to run the optimizers, right? And the idea again is that what you expect to get from the optimizers are series of sets of parameter values. So if the optimizer is giving you the parameter values, then as a modeler, your responsibility would be to simulate the model and then calculate what the difference between the model prediction and the data is, and then return that difference, that error, for those parameter values back to the optimizer, so the optimizer can make a intelligent guess of what the next set of parameter values will be, right? And this is what we call writing a cost function wrapper. Again, the idea is that we have to somehow connect what the optimizer is giving us to running the simulation, estimating the difference between data and parameter values, and returning that difference back to the optimizer. So exercise 5.2 here does a little bit of that. Again, we as we did in previous exercises, we're not gonna use we're not gonna be using real data in this case. We're gonna use what we call synthetic data because we generated ourselves, so we know what the ground truth is for the parameter values. We do need the estimates that we did in the previous part, because as we mentioned, we will, depending on the optimizer that we're using, we might need to have a good guess of what these original parameter values are. So I basically summarized all of the steps that we did in the previous exercise here in this cell. So it gives me all of the estimates of the parameter values based on the synthetic data that we generated. So now we can start defining our objective of or cost function, right? And this, based on how tellurium works, the idea is that this cost function has to do 4 things. It has to load the model. Once the model has been loaded, so we have to define what the model is, right? In our case, it's going to be an SIR model. Once that model has been loaded, we have to, because the optimizer is giving you the parameter values, right? So we define this Python function called cost function that takes in as an input a dictionary of parameter values, a dictionary that has the parameter and their the parameter name and their corresponding values. So given that data structure that has been passed by the optimizer, we need to assign for each parameter in the model, the value that is passed on by the optimizer. And this is what these lines 5 to 8 are doing. So we look at the value we look at what the optimizer is passing as a dictionary, and then we assign for each parameter in the model, we assign a value that it's given by the optimizer. And then we have to simulate the model. And that's what we do in this part. So we've already loaded the model, assigned some parameter values. Now we can simulate the model. And then we have to calculate the residuals. And this is what this part is doing here. So the reason it looks a bit complicated is because depending on how you're slicing the time, what the time points are in your model, they might not one-to-one corresponds to the time points in your data. So what this part of the code is doing is try to find, let's say in this particular case, you simulated the model, let's say by 100 points. So you have 100 points of simulated model prediction or model results. So we go over these points and we look which point is closer in time to the times the experimental data. So that's what this part is doing, this part up here. Basically looking at which points are in time closer. They might not be one-to-one. So let's say you have a data, what I'm trying to say is, let's say you have a data point that was collected at time 10. But because of the, at day 10, but because of how the model is being simulated, the model does not exactly has a point at day 10, the model result. It has a model, it has a prediction at day 10.5. So what this part of the code is doing is saying, okay, look at which point is closer to the time point in the data, and then take that to calculate the difference. Once I calculate the difference, I use the chi-squared, where I am squaring the difference, and then I adding over all of the data points, which I'm iterating over here. And then that gives me the residual that I have to pass back to the optimizer. That's why this that it returns this variable called diff. Notice that this part of the code I used so it can plot. So every time the optimizer passes a parameter value, you can see how what the model prediction is for those particular parameter values. So it's a way of seeing how far you are from the model prediction. There's documentation, the library that we use to run these optimizers is called LMFit, and there is it's a publicly available library. You can look at if you are interested in what the in the documentation of the library. You can access it here. And the remaining parts are going to be based on what this documentation requires users to do if they want to fit them, if they want to use one of their optimizers. So again, the idea here is that this cost function, we've defined a function that is intending to return the difference between the parameter that takes in from the optimizer and the experimental simulate the model and pass pass the error back to the optimizer. So this is what these steps are doing here. As you play with this code, it will become more obvious what it's doing. We could break this into different functions. We just wanted to keep it this way because in this linear format, it's very obvious what each part of the code is doing, but you could potentially think of this as a separate part of the code, this as a separate part of the code, and so on. So now, the first thing we will do is that based on those estimates that we did in the previous exercise, we want to compare how far we are from how far are our estimates from the experimental data or the data that we generated here synthetically. And the way we use this LMFit library is that we first define this to-fit list that contains the name of the parameters that we want to fit. And then we create this object called a parameters object, which is basically it's going to contain all of the parameters that you want to fit, that you want the optimizer to be able to estimate. And so once we created this parameter object, we can add to this parameter object every parameter that we want to estimate. In this case, we want to estimate the parameter S1 and see that we have to give an initial guess of the parameter value. We're giving the, or in this case, it's the parameter S0. We're giving the value of S0 that we estimated in the previous exercise. And notice that we also, this is something we discussed earlier, we have to tell the optimizer what is the ranges over which we will allow this parameter to vary, or that the optimizer, what are the ranges in which this optimizer is going to look for parameter values. Again, because we know that we're very close to the solution, we allow the optimizer to explore the space over 100-fold change of each of the estimates that we're already passing in. And we do the same for beta and for K1, which is mu. And if we call our cost function with these parameter values, notice that I can now pass these parameter objects, because this is what the optimizer is going to be passing to the cost function. I can pass these parameter objects to my already defined cost function, and it will generate a model prediction based off on the estimates that I had. And then I can see how far I am from this, how far is my model prediction from the data. And anyone has a guess of what this number up here is? It's also here, so it means it's what is being returned by this call. Any ideas? So we said that the cost function returns to the optimizer the chi-squared, which is the distance, a way of quantifying the distance between the model and the experimental data. So that's why our cost function is returning, right? If we went back here, we calculate the residuals and then we pass the error to the optimizer. So we're passing to the optimizer, we're passing the chi-squared, which is a number that tells me how far is my model from the data, right? So basically that is the value of chi-squared given what the parameters are, what my original parameter estimates were. Okay. So then once I've initialized my parameters object, then the next step is to initialize the minimizer. Again, optimizer, minimizer, we can use them interchangeably here. And we use them, see that we have to specify both what the cost function is going to be, right? The cost function that we defined already, and the parameter object that we created, because that contains the information of the initial cases, the range, and the names of the parameters that I want to fit. And then I choose an option here. I have to choose a method to call the optimizer. I can call the optimizer by calling this method here, the minimize method. And the method that I'm choosing here is called Nelder. Does this one sound familiar based on what we talked about earlier? Which is this method that we're looking at? Well, first question, is this local or global? We talked about, we mentioned 5 different methods. We talked about gradient descent, Levenberg-Marquardt, simplex method, simulating annealing, and genetic algorithm. We did say that the Nelder method is also called simplex. So this is that optimization algorithm where the simplex is created and it starts contracting or reflecting the simplex to try to reach the solution. And this one is in particular is a local optimizer. So if I run this code, I should see what my optimizer is trying to do. And can someone tell me what it's trying to do? What did the optimizer do compared to? Remember that this was where we started at. This is the initial guess that we gave. And then the optimizer did something and ended up here. What did it do? So the optimizer was trying, right, different values of the parameter of the different values of the parameters to try to minimize the distance between my model prediction and the data. And again, how it generated the next set of values given what it started from, it's based on the Nelder method that we talked about earlier. But we could choose different methods too. For example, I'm not exactly sure. Let's not exactly sure what the call for the gradient descent is, but we could try a global method. And then you can see that with a global method, the optimizer is actually exploring very different regions of the parameter space. And that's why the difference between the model prediction and the data is so big, at least at the beginning, because the optimization algorithm is just searching or sampling the parameter space more widely. But eventually, we would expect even this global algorithm to find a solution to the fit between model and data. The only problem about these algorithms is that they might take longer time. They are more computationally expensive because the assumption here is that we didn't actually know that we were close enough to the actual solution or actual ground truth of the parameter values. So we have to ask the optimizer to look the parameter space more thoroughly. So can anyone, because I don't wanna change. Could anyone go here to this web page, and then if you click on minimize, it'll tell you what the different calls are for all of the different methods. Can someone get me what the gradient descent call is? Or I can try doing it in my phone as well. In the meantime, I'm just gonna let that dual annealing method run, and you can see how the model, how the optimizer is trying to find a combination of parameter sets that minimizes the difference between model and data. And you saw, now we're pretty close, but you saw that that this algorithm was basically all over the place. It was jumping back and forth because it was looking for, it was trying to explore wider ranges of the parameter space. So yeah, they don't even have like gradient plain gradient descent in their options. They always use the Levenberg Marquardt because that is a more robust, and it's not that different from the gradient descent. It's just more efficient. So could I ask someone to run this same code, but instead of here method, in method they can type least sq for least squares, least sq, and run it, and then tell me what you're seeing. So here again, what we're doing is that we're trying different optimization methods. You see that this one is taking a little bit longer to converge, but again, it's taking longer because the algorithm is designed to explore the space thoroughly and try to avoid minimas that are not the best minima or the best solution. I'm gonna share the poll again just to see whether people are running their own versions. So while this runs in the background, I can go to the documentation. And if I go to minimize, I can see what the structure of the minimize function is. It takes the objective function, right, as a argument. It takes a parameters object that contains the parameters of the model. And then it also takes the method that we're going to be using. And here are some of the methods. We just did, here we just, in class, we discussed the Levenberg-Marquardt. We discussed genetic differential evolution is a version of the genetic algorithm. Bayesian hopping is one type of similar to the simulated annealing, but they also have simulated annealing or dual annealing. But there's, of course, many other different methods that could be used. And the documentation here explains what the method is doing. And also Herbert's chapter explains additional methods that we did not discuss in class. Okay, I'm not gonna wait for this one to converge because again, it's both stochastic and global, so it might take a long time for it to converge to the solution. But but this gives you an idea now of the difference between using a local and a global optimizer. And again, yeah, so this was just as an example. Let's try the least squares here. Again, because we're still starting from a yeah, I'll have to see what the problem with the inputs are. Usually some of them require you to pass like the sum of the difference. Some of them require you to pass a list of the differences, and they do the sum themselves. So that might be a little bit of difference here, but if we use the Nelder method, that is guaranteed to find a solution because it's a local optimization algorithm nearby that already a good guess. And when the optimizer finishes, it returns the, it compares the estimates of the parameters versus what the original guesses were. And here you can see that we started at the estimates we had from the previous exercise. And then we see that the optimizer refined those estimates and give us something much closer to the ground truth than what we did by looking just at the by estimating it ourselves by looking at the different parts of the curve. And then we can, once we have these parameters, we can again use, we can estimate what R naught is because we have beta and mu. And now we have estimate of R naught that is 4, which is much closer to the actual number based on what the ground truth is. Something I wanted to do that is not in the exercise is to try to see how well this will do if we have incomplete incomplete data. So what I'll do is that the active cases, well, what I can do actually is so I'm gonna just simulate the model. No, 10 is still a lot for 5 days. So instead of having the whole data, now what I have is this. And I want to, so now I just have that part of the data. So I want to see how well the model is able to fit that, how well the optimizer is able to fit it, and what the estimates are based on the fact that we have incomplete data. And again, what I'm trying to sort of like simulate here is the fact that at the beginning of the pandemic or the epidemic, you might not have complete data, right? Because let's say this is like 50 days into the pandemic. But by this point, you already sort of like know that you're approaching a peak because the rate of daily new cases is sort of like slowing down. So it's still a pretty good guess based on, so we have still a lot of information there to be able to estimate. Let's do 3 to 8. Yeah. So even there, I think it's still gonna find a good solution. So because we already had, and this is because we already have a good estimate of what mu is. If you use a local optimizer, right, we will still see how the quality of the guesses is decreasing as I have less and less data. And that is because, of course, the more information you have, the better your guess of the parameters will be. And like if you actually have that tail part of the curve, your optimizer will also be will have better idea of what the parameters are. But again, the thing here was that we started with a pretty good guess of what the parameter values are. And we're asking the optimizer to do a local search around that area. And when we do that, the optimizer is always gonna find a solution. What do you think will happen if I, instead of using a local optimizer here, I use a global optimizer? Because the global optimizer is way less dependent on what the values of the initial guesses are. Any ideas? I mean, you can run it yourself. If you, if what I did, maybe this is because as an exercise, as a homework exercise, but you can cut off the data and then call a global optimizer, let it run for a little bit and see whether the optimizer is able to find a solution or not. My guess is that a global optimizer will have a much harder time finding a good solution to the model if we have this limited amount of data. And this is important, again, coming back to real life, because like what you want to do at the big is that if you want to use an SIR model to estimate the parameters or use the data, actual real data to estimate the parameters of an SIR model, you certainly, and to make decisions based on those estimates, you certainly want to make those type of parameter estimates as early as possible, because if you're already past the peak of the epidemic, you basically containment measures will have very little effect on what the rest of the pandemic or epidemic looks like. But if you're able to estimate some at the very early stages of the epidemic, then you will have, for example, a good idea of when do you expect a maximum number of individuals to be infected, at what time, what that number will be, and so on, so on. And this is a little bit of a simplification because of course, probably, well, I think you will be surprised how much information you can actually get out of an SRM model in real world. I think some people have shown that you can actually use it for do pretty good estimates. Okay, I'm gonna launch a poll now again to make sure that everyone has been able to, at least to run their code. In the meantime, I'm gonna show the remaining of the, I think I closed the, yeah. The remaining of the application I was using, the last part of that application does exactly this. After you estimate the parameters mu and n times gamma or beta, then it runs a local optimizer to give you a sense of what the parameter values are for different data sets from the real world. So let's do this quickly again. Again, remember to estimate. Let's do it with the case data from Italy. First, estimate mu by looking at the tail end. Then we estimate beta by looking at the leading edge. Then we calculate R naught. In this case, it's 8. And then we can simulate the model, see how far we are from the data. We're pretty close. And then now we can feed the model to the data. And we see how the model is trying, how the optimizer is fitting the model to that data based on our original estimates. And the reason I'm showing this example is because in this particular case, this is real data from real experiments. Not in real experiments, from real actual cases recorded in Italy at the beginning of the epidemic or the pandemic. And again, this is using the simplex method, the same we're using in the code that we showed in class today. I'll come back and make sure to look at why least squares is not working. Again, I'm pretty sure that I have, it's because I probably have to pass instead of passing the sum of the difference, I have to pass the difference for each data point. Some of them have like minor details. Right. So again, when we look at the exercise here, we see that the model, because this is synthetic data, has no basically no error in it. The model is able to fit pretty well.
Josh, yes, the least squared, for some reason in NumPy, the least squared doesn't use the residual. You pass it the list.
Okay, that's an easy fix in the code that I had, but yeah.
But it has a different call from everything else. Right. I don't know why.
Right. So here you can see when this is finally ran, it sort of refines the parameter values, and then from the estimated R naught that we had at the beginning, which was 8.20, now we have a fitted R naught that is 3.69, and then we estimate from this data that people remain in an infectious state for 26.43 days. This might not be entirely correct because the SIR model might not be entirely correct, even when we consider the first wave. We know that people can be infected, and usually there is a latent phase where people are infected but not infectious, And that complicates the mathematics of the estimates, but it will probably give you a better sense of how long the infection actually lasts. Okay, so everyone seems to be with me. I would encourage you to, if you want to get a sense of all of this, just go to this app in NanoHub, try different data sets, try even getting incorrect versions of, so what if I do this to calculate mu? Yeah, I'm like a pretty far off. Look at what my estimate of how long the infection lasts. It's like almost a year. So get a sense even by getting incorrect choices to get a sense of how that affects your estimates. The last thing I wanted to cover is that sometimes we can use additional data sets. So let's say that we have not just we have not just data for what the active cases look like, but that we also have data of what the recovers look like. So we could potentially add additional data sets, and that's pretty easy in the code that I gave you. In the code that I gave you, we were just looking at the difference between active cases and infectious individuals in our model, but we can also look at the difference between uninfected or susceptible individuals. And we can also look at the difference between recovered individuals in the actual data and the model predictions. And we just have to add each line of the code by specifying what is the data set that we want to compare and what is the variable in the model that corresponds to that data set. And then based on those estimates, see that even though we estimated the parameters for the active cases data, we infer the dynamics of the whole system because we have inferred all of the parameters of the model. And then we can run the optimizer. And now the optimizer is not just trying to fit one single data set, but it's trying to fit the three data sets at the same time. Right. And look that when I have again, and I look how close we are to the actual ground truth. So now we're actually getting the right results, and this is again because additional data means that you have a better estimate of what your parameter value says. Real world data is never as perfect as this synthetic data that we generated. It usually has some noise due to measurement errors. But we can still fit the model to the noisy data. Even when we look at even if we were to do the estimate ourselves, even though they're noisy, they still look pretty linear on in these log plots. So we could use even though it's not a perfect line, we can still use this to try to get some estimate of the parameters. And once we have those estimates, we can, I'm sorry, I need to rerun this because all the data I have. Right. Once we have those estimates, I can try to fit the model to the data, even if it has a little bit of noise. So in this case, the data is not perfect as in the model prediction, but the optimizer is still gonna try to find the best fit given the noise. And now we have a certain different values for the parameters of the model, and that's because of the added noise. right? You wouldn't expect the parameters to be exactly the same, given that we've added noise to them. And this last part of this code, what it does is that it tries to fit the model, the same idea, fit the model to different data sets, but in this case, all of the data sets have noise, and still see that even with noise, we're also very close to the ground truth. And that is because we have additional data, and additional data means better estimates and more confident on the parameter estimates that I do. Okay, so that's what I have for today. I'm glad we were able to go over it. We will generate some homework exercise based on what we've talked about here. And if you have any questions about what was discussed here or the homework, don't hesitate to contact me or James. And I'm gonna head back to James. I'm gonna hand back to James now.
We're just perfect. That's great. I hope that was helpful to people. And there'll be a homework problem which Josh and I will work on tomorrow to generate, which will give you the opportunity to try out some fitting and explore that. Thank you very much, Josh, for the lecture. Really appreciate it.
Yeah, no problem.
Any questions before we break?
So on Canvas, there's the homework, and then there's another assignment about finding a model to be simulated in class or something.
Right. So that's something that for next week, if you could do that.
Okay.
One of the things that we will do is we'll do some to help get people ready for their projects. One of the things that we did last year, at least, was we took some published models and worked them up in class to show how the process of taking a published paper and then reproducing it. And we have some that Josh and I like, which we can do. But if people in the class can suggest some models that would be interesting to replicate, probably not the one that you're planning on doing on your class project. But if you decided you're going to do a class project on one paper, and there was another paper that you saw that you think would be reasonable to try to reproduce in class, shouldn't be too complicated because you don't want to take more than the class time. That would be great.
Okay. Yeah. Thank you. I was looking at that assignment all week, thinking that it was just the proposal again. Back a week.
Right. I guess I should have been clear about it. The idea was that the project is you're replicating a paper and then extending it. But we wanted to practice together on that. We get a sense of how to look at a paper together, how to find how to see whether the results are reasonable, those kind of things. So if people find something that's interesting, as I say, Josh and I have found some papers over the years that work pretty well. But if people find a paper that they say, wow, that's not too complicated, it would be really interesting to see how to put that together, that would be very good.
Okay.
So that was
on that. Thank you.
Okay, great. Thank you for asking. Anything else? No? Okay, Josh. Well, thank you again. And I'll see everybody next week. If not before, please feel free if there are questions.